네, 오늘은 지난 시간에 이어서 continuous time pricing equation이 어떤 식으로 이제 결정이 되고 어떠한 의미를 갖는지, 어떠한 경제학적인 의미를 갖는지에 대해서 좀 더 자세히 보도록 하겠습니다. So today we will continue on continuous time pricing, and we will try to understand how the pricing equations determine asset prices. So this is what we got last time. So the pricing equation is given in this fashion. So the first term here is the drift term based on the dividend. So this is the, well, given that gamma is the pricing kernel, and this is like the stochastic discount factor. So gamma t then is gamma t times dt is, this is discounted dividends, okay? And this quantity is discounted price. So what it's basically saying is that if we arrange the terms a little bit, conditional expectation on infinitesimal change in this thing. So what is it? That is the discounted price, and the drift of that term is going to be negative of discounted dividends. So what it's basically saying is that discounted price is going to drift at the same rate as the negative of the dividends. So if the stock is paying a lot of dividends, then the expected drift of the stock is going to be lower by that amount. And this condition is useful later to get the pricing PDEs. So we will multiply discount rates, pricing kernel to the value that we want to price, and then apply the Ito formula, get the drift, and the drift should be the negative of the discounted dividends. Now you can compare this with the discrete time version of the pricing equation. In that discrete time version, we had price equals expected value of m times m. Okay? So why is this the same as the continuous time version? What is the analogy here? So you can understand that as m0 in the discrete time version of the pricing equation as the following way. So you can also express it the pricing equation in this fashion, right? And we will set the current level of the pricing, the discount factor as 1. Then what it's basically saying is that current price is simply the expected value of the future price, right? So this is, and then if you rearrange the terms, then you can get the following. 0 equals expected value of the change in M1 times P1. Okay? So you can see the analogy here from this equation and that equation. Okay? Because we assume in the discrete time case, there's no dividends. So the drift, when it's discounted using the stochastic discount factor, the drift of the M times P is equal to 0. Now you can rewrite D times lambda plus P into the following fashion. How do we do that? We just apply the Ito's formula. Remember, the Ito's formula says if you have the product and if you want to take the derivative of that, what Ito's formula is basically saying is that do almost the same as when you do it for the discrete time case, deterministic case, but then you also have to consider dx times dy, because dx times dy might not be zero in when dx and dy has diffusion process in it. So we apply that for the case of the discounted price in the continuous time case. Then we got the following: d lambda times p plus lambda times dp, d lambda times dp, and then you divide by lambda times p on both sides, and then you will get the expression here. Okay? And then you take the, of course, you take the expected conditional expectation on both sides. In other words, what was the pricing equation? The pricing equation was that conditional expectation of the change, infinitesimal change in lambda times p should be the same as negative of discounted dividend times dt. Okay, so what I did in the previous slide is basically apply Ito formula here. Then you will get this pricing equation here. This pricing equation is basically telling you the following. What is this thing here? This and that combined is going to be expected return y, because return DRT can be expressed in the following fashion: dpt over pt plus. Okay, so that's going to be the return. And how is, so basically this this equation is telling us is how the expected return is going to be determined in this continuous time pricing case. Now there's one more complication, which is this term here. Okay, so that is like the infinitesimal change or the drift, okay, drift of this diffusion process, right? And that drift of the diffusion process is basically the same as the risk-free rate. Okay? That is the same as the risk-free rate. How do we see that? Well, the pricing equation above, so this pricing equation should also hold for the risk-free rate. Should also hold for the risk-free rate as well, or the money market account. So we plug the money market account into the pricing function. In other words, so we are treating the money market account as one asset. I'm just rewriting what is in the pricing equation above using M instead of P. Now, what you can find is that for money market account, dividend is 0. So this term is 0. And also, the money market account doesn't have any diffusion process in it. It only has dt. So when it's multiplied with d lambda, it should also be 0. So what is only left with is dm times m equals negative of expected conditional expectation of d lambda over lambda, which is the diffusion of the drift of the stochastic discount factor or the pricing kernel. And what you can see is that because this is the same as the risk-free rate times dt, therefore, in the continuous time case, the risk-free rate is determined by the drift of the stochastic discount factor. And this is very analogous to the discrete time case where we calculate the risk-free rate as the inverse of conditional expectation of the stochastic discount factor. So there's an analog here. Now, using this definition of the risk-free rate, you can rewrite the pricing equation here this pricing equation, you can rewrite it using the risk-free rate that is given here, and this is what you obtain. Okay. Now we will bring in the consumption asset pricing framework here. So let's define the pricing kernel using the utility function and the consumption level. In other words, it's going to be discounted value of your marginal utility. Okay? So that's going to be the pricing kernel from now on. Okay. Now let's get this value here. Okay, d lambda over lambda, okay, using Ito's formula. So what do we have to do? The thing we have to do is to calculate d lambda, and lambda is simply the product between these two terms, okay, and you can apply the Ito. Okay, now the key here is that there's d times e delta t and d of u prime ct, but then the key is that this term, both of these terms are zeros because, well, the second one is not zero, but because it is the first term here only depends on t. So when you take the total derivative of that and multiply with another total derivative, that is going to be zero no matter what. So you only have these two terms, the first two terms, and I'll leave it to you. I'll leave the detailed calculations to you. So by applying the Ito, you can calculate d lambda t. Okay. And it is going to be like this. If I tell you one more trick, where is this from? That is going to be obtained from d of u prime ct. Okay, so you should also apply Ito formula here, and what you will get is delta u prime delta ct dct plus 1/2 a half times the second derivative of the marginal utility with respect to ct times dct squared. Okay, so the second term here, the whole second term here is basically this du prime component. Now you just rearrange the things after the first line of the calculation, obtain the second line, third line, and so on. Now use the definition of the relative risk aversion, lambda t, and also eta t. You can rewrite the pricing equation in this fashion. Okay. And also you can obtain the expression for the risk-free rate like the following. Now, how did you obtain, how did you do the detailed calculation? You used the previous property, which is this one here. Okay. In other words, just the drift term of negative of the drift term of the stochastic discount factor is going to be the risk-free rate. Okay, and using the definition of the risk-free rate and the consumption-based stochastic discount factor, you can rewrite the continuous time asset pricing equation in the following way. So basically, you're using this property. Okay? You're using this property, plug into the one of the previous equations, and you will obtain this beta pricing model in a continuous time version. So what it's saying is basically the following. What is the first term here? This is the expected return on the stock. So this is the expected return on the stock, and you're subtracting the risk-free rate so that on the left-hand side, the whole term of the left-hand side is the excess return on the stock or the financial asset. And on the right-hand side, what you have is the risk aversion coefficient times this this term here, which measures the covariance of the stock return with respect to the consumption growth. Okay, so this is like covariance between consumption growth and return. So what it's saying is basically the following. We obtain the same intuition as we learned for the case of the discrete time. In other words, assets that covary more strongly with consumption will get higher average returns. In other words, suppose there's an asset that pays more when the consumption growth is high, or an asset that pays low when the consumption growth is low. These kind of assets are not very desirable because it doesn't work as an insurance. Therefore, these kind of assets, unless they provide higher expected returns, investors don't want to hold. Okay? Therefore, their prices are lower and their expected returns are higher. Conversely, if you have an asset that covaries negative with the whose returns covary negative with the consumption growth, this kind of asset is going to pay more. I mean, their returns are going to be higher when the consumption growth is low and negative. In other words, during recession or when things are bad, such returns will have, such assets will pay off more. Investors value such assets because they work as insurance. Okay? So their prices are going to be higher. Therefore, their expected returns, even though they are not very high, investors are comfortable with that. Okay. Now, we can also calculate the Sharpe ratio from the equation given here, Now, using these expressions, for example, the drift of the stock return is basically this. Okay, so the first term is the drift of the stock return, and this term is the variance or the standard deviation of the return. And the third term is basically the variance of the consumption growth. Okay? Now, because the second term in the previous equation, this one, expected value of CT times DP is basically the same as covariance between in consumption time, and that is going to be the same as the correlation between C and P times delta C and delta P, right? And because correlations are between negative and positive one, we can obtain this bound for the Sharpe ratio, which we also obtained for the case of the discrete time finance. Basically, so there's a very strong analogy between the discrete time case and the continuous time case. Now, let me summarize what we have done so far, okay? Especially in terms of the analogy between the discrete time and the continuous time. Now, the present value, the price of any asset is basically discounted future cash flows. Okay? So if when suppose X is the future dividends, X here is the, XT is the dividend stream. Okay. So given the dividend stream, basically current price is the discounted value of all future dividend streams. What is return? Infinitesimal return on a stock is basically the sum of the two things. The first term is the infinitesimal change in stock return, percentage change in stock return, I mean. And the second term is basically the dividend yield. A cumulative value process is basically dVT over VT. In other words, suppose the value is V, right? And what is the percentage change in value? That's going to be delta V over V, right? And this is like, infinitesimal return if you assume there is no dividends. Risk-free rate is given as R times dt. Excess return on a stock we have seen many times, which is DRT, that is the infinitesimal return, minus the risk-free rate, and that is going to be the same as the thing on the right-hand side. Now the analogy analogy of the pricing equation in the discrete time is basically that the continuous time equation that we learned last time. So in other words, in the continuous time case, discounted price, the change in discounted price should be the same as, okay, and here we use X instead of D. Therefore, you divide by lambda P on both sides, and then you get that. And for the case of the value, if you assume the dividend is 0, then you get the following. And we also saw how the risk-free rate is determined based on the stochastic discount factor. So there's also, again, very strong analogy with respect to the discrete time case. In other words, in the discrete time case, risk-free rate is the inverse of the average value of the stochastic discount factor, whereas in the continuous time, the risk-free rate is basically negative of the conditional expectation of the stochastic discount factor. Now, there's also another analogy similar to the continuous time case. Discrete time case. In the discrete time case, the excess return on a financial asset is basically determined by the covariance of that covariance of the return on the asset and the stochastic discount factor. And we have something similar in the continuous time case. And we can also do similar exercise for the consumption time, consumption-based asset pricing model, and we get the stochastic discount factor in this fashion. And we get the risk-free rate in the consumption time, consumption finance, and also Sharpe ratio and the expected return using the consumption growth. So there's a very strong analogy between the discrete time and the continuous time. So even though continuous time math can sometimes sound challenging, but if you consider the discrete time analogy, it is easy to understand.